All right, in this exercise, we have a truck pulling a car along a horizontal roadway to give us some tension in the cable. And we want to know, there's a few parts to this. In part A, how much work the cable does on the car if it pulls horizontally. So just a little picture here. We have our roadway. Here's the truck, right? Here's the truck here. And here's the car over here. And then there's the cable kind of attaching them, right? Truck, car, and then if the truck is pulling the car, then this is the velocity in this direction, right? If we do a little snapshot, kind of a free body diagram of this the car, then there's a force of a cable acting on it, right? So this is like my I'll just call this the F, and this is equal to 850 newtons. And we have some other forces here. Clearly, there's the weight of the car, right? So the mass of the car times gravity. We also have a normal force here, right? Okay, so we want to know for A, in this scenario here where it's pulling horizontally, how much work is done by the cable. So I'll just say cable on the car. So cable on the car, right? So this kind of sets up what, if we want to, free body diagram, something to see how that force acts on it. It would be a free body diagram of the car, and then how much work is done by this force on that, right? So free body diagrams have, forces acting on something here, right? So kind of did a little free body diagram of the car, and then I have my cable force as well as the other forces acting on it there. Okay, so work is the component of the force parallel, right? So we have kind of the easiest way to set this up is we have the work is the component of the force parallel to the displacement times this displacement. So I'll call it S is my displacement here, or call it a D if I wanted to. Right, so this is how far it travels, and this is the component of the force that is in the direction of that displacement. Okay, so we have some displacement. The car is going to end up 5 kilometers. So over this whole thing, the car ends up way over. Let me get rid of this truck here. Now we're on a much larger scale, and the car ends up being over here eventually 5 kilometers away. Or we want everything in meters, right? So this is 5,000 meters, right? 5,000 kilometers, or 5 kilometers, 5,000 meters. Okay, so we have our displacement there, and now we need the component of the force parallel to it. Well, the displacement is off to the right. If I set up a coordinate system here, positive x, positive y, my displacement is off to the right, my force is off to the right. They're in the same direction. And so when the truck pulls horizontally, this is pretty straightforward. I just have my 850 newtons times my 5,000 meters, my 5 kilometers, and we end up here with, this is 4.25 times 10 to the 6, 4.25 million joules of work done if this tow truck pulls it 5 kilometers. It's like 3 miles, barely over 3 miles there. So that's what it would be if it pulls horizontally. There's also a question of what is the work done? And by the way, this is the cable on the car. Note here in my coordinate system with a positive x to the right, I had a positive 850 and a positive 5,000. So I got a positive work done by the cable on the car. What we've seen from work energy theorem lecture and whatnot, that's going to lead to an increase in energy in the car, right? Because the cable is doing positive work on it. But that's not what this question is asking. There's a kind of a second part to part A. What if it pulls at 35 degrees above the horizontal? Well, I still have my 5,000 meters, so let me just change this figure a little bit. And now the truck pulls up at still 850 newtons, but at an angle 35 degrees above the horizontal. Okay? So now my displacement is in the positive x direction, right? But the force isn't only in the positive x direction. I'm back to breaking forces into components again. So I have some component of my force like this is like a y component, and I have a force over here, my x component, right? So because my displacement is strictly in the x, that's the way I set up my coordinate system, only the x component of the force is going to do any work. If I had displacement of the car off like this, then the entire force would do work. But hopefully, our tow truck doesn't make the car fly in the air, right? So that doesn't happen. It goes along the roadway. So we have the force in the x direction. Well, this is our x component. We're 35 degrees is off the horizontal here. So we have Fx is equal to f cosine 35, or 850 cosine 35. So now in this part we have the work done by the cable on the car is going to be equal to, this is f cosine 35 times 5,000. So we have 850 cosine 35 times the 5,000 meters. And this comes out to 3.48 times 10 to the 6th joules, 3.48 million joules. So less work was done, on the car at that angle, because not all the force went into doing work on it. Because it didn't displace in the vertical direction, so the vertical component of the force didn't actually do any work there, right? The displacement was just in the horizontal direction. Okay. Now in part B, it says, what is the cable? How much work is done? How much work does the cable do on the tow truck in both cases of part A? Well, the tow truck is over here, right? It's like just attached to it, and so we kind of look at the way that here's the truck, right? So if I were to free body diagram the truck over here, then I have the cable pulling out. There's still a weight of the truck. There's still a normal force acting on the truck. But then the cable was pulling back this way when it's horizontal, and it was pulling down, this way when it was, at 35 degrees. And the truck is still moving in the positive x direction. So it was moving this way, but the force is back that way. Right? So we have basically what happens when we look at the work done by the cable on the truck in the horizontal case is that the force was a negative, but the displacement was a positive, and therefore making this a negative work done on the truck. And then we have in the case where it's up at 35 degrees, we had again negative 850 cosine 35 times still a positive 5,000, right? We could have flipped this around. We could have flipped it around and said, oh, you know what? Let's call positive x to the left, right? That way my forces are positive. But even if we did that, displacement would be negative then, right? So we're going to end up with a negative work done. Anytime we have the force opposite the displacement, we have negative work, right? So, the work done by the cable on the truck is opposite the work done by the cable on the car. And actually, if you think about it, if you have a truck pulling a car and the cable stays tight the whole time, that's an important feature there, then the whole system, the truck and the car, would actually kind of move off together, and there's no increase in energy, because if you add these works together, and this is going back to the work energy theorem, if you add those works together, you get zero. So the net work done on the truck plus car plus cable system is zero. So you don't have extra energy going into one relative to the other. They're just, the sum of the energy is still equal to zero. But again, that's maybe come back to what I just said there after doing some work energy theorem problems. And then part C asks, how much work does gravity do on the car in part A? Same amount of work that gravity does on the truck in part B. If gravity is acting down and my displacement is this way, regardless if that's pulling up at an angle or down at an angle or horizontally, or even if the tension is pulling like this, which in which case there wouldn't be any displacement. If my displacement is off to the right, but my gravity force is down, no work is going to be done, right? Because there's no component of the work in the direction of displacement, right? If I say here, the work done by gravity on the car, well, this is going to be, the component of the weight parallel to the displacement, right? But the displacement this is just in the x direction, this is just in the y direction, so this is 0, right? Because any way you look at it, either way, you could really look at it either way. If I look at just the x direction, and this comes back to, we always break everything into components first. If I just look at the x direction, my displacement, I have some displacement, but I have no force, right? So it would be here 0 times s, right, in the x direction. Or if I look at it in the y direction, I have a force, so I got y, or mg. I got a force, but then I don't have a displacement. So you get 0 kind of either way you look at it there.